Okay, time to start. Just to check, I'll get you. Jordan, not here. And Utah, not here. Okay, James, you had a question? Yeah, oops. Yeah, you told me that you two go by the same name, so.
The homework, is that due Wednesday?
Okay, and this, I think it was Katie brought up. I just out of reflex put the homework due on Monday, but I will shift it to Wednesday. So is that what, homework 26 or 27?
26.
Okay. Sorry about that. It was just a reflexive thing to make it do the next class period after the lecture. Okay, so today we are going to be reviewing for the exam. The exam will be over chapters 9 to 12. A student sent me an email over the weekend asking about when the exam is, the same time as always, in lab on Tuesday. So some reminders, things to make sure you get all of the credit you can, because as you probably know, the goal of the exams from the teacher's perspective is, number one, to gauge how much the students have learned, and number two, to try to get them a good score, right? Because when students don't get good scores, it's painful for everyone. So make sure you include a figure on all of the problems unless you're specifically told you don't need one. And even then, it doesn't hurt to have a figure, because like on the first problem on the last exam, I didn't require you to put an additional figure, but it generally was helpful to draw the forces as free body diagram so you can break them into components and so on. Okay, second thing here, make sure you include concepts for each problem. I know I've said this a lot, but still, there was like one exam that I graded over the weekend that didn't say a single word until it got to problem 5. Not a single word, problems 1 through 4. Well, that's a huge amount of points lost. And the student had to have had some knowledge about what was going on, but if you don't give it to me, I can't give it a grade. The last one, something I mentioned last class period, make sure you show your physics understanding when solving the problems, right? Just being able to pull an equation and put numbers into, that's not physics, that's math. The physics is identifying the principles that are going on and putting them together. So an example where this happened a lot, on the problem with a car rounding a corner, you have your free body diagram, force of gravity, the force normal. The useful choice of directions would be having one direction parallel to the acceleration, so I call it the center direction, and one perpendicular. And then you say, well, what's going on here? What's my physics? And your physics had just two things. Newton's second law, sum of the force vectors is equal to mass times acceleration. And if you're going in a circle, then you have to have the acceleration in the center, that's toward the center of the circle, is v squared over r. And so then you put those together and did your math from there. But the physics was identifying these are the things that are going on and putting them together. And there were a lot of people who simply had an equation that was, tangent theta is equal to, and I don't remember what it was, something like v squared g over r. Now that has horribly wrong units, so it couldn't be that. But they just had an equation that they'd apparently memorized with no physics involved. And so, you get a really minimal score because you bypassed all of the physics and just went to the answer. So make sure that you show your physics in your solutions. So any questions about these reminders? I want to make sure it's clear, right? Higher scores are always better, and understanding what's expected helps you get higher scores. Any questions? Mahala.
On the practice exam,
yeah.
Momentum is on there. Should we expect that to be included on this exam?
With practice exams, different years, I cut things up differently, so they're broken up in different ways. So this will be over chapters 9 through 12, right? Like last year's exam was over, I think, chapters 8 through 10. And so there's more stuff on the higher end. And yeah, so no, momentum is not a specific topic covered. Now, it can come up in a problem, but it's not a specific topic, so it's not going to be a focus of a problem. Okay, so let's start with review. Chapter 9. Chapter 9 was studying equilibrium, or as my engineering students are taking a class all semester long, statics. Statics is taking equilibrium and going in a whole lot more depth than we ever do here. And so what kind of things do we need to know for the exam from statics? Well, first of all, we have what equilibrium means. The word itself, equilibrium, equal forces. But it's actually a little bit more than just equal forces because you had two conditions for equilibrium. The two conditions were sum of the forces equals 0 and sum of the torques equals 0. Now those are vector equations, so in fact, since you have three independent directions, you could have a maximum of 6 equations from those two. Some of the forces in x direction 0, some of the forces in y direction 0, some of the forces in z direction 0, and so on. Obviously, you're not going to have problems where you're having torques and forces in all three directions. But it's just something to keep in mind that it's not just a one-dimensional equation. So with this, that implies by Newton's second law, acceleration is 0 and angular acceleration is 0. So when I look at a problem to determine if it's in equilibrium, the first thing I do is I look and say, is it accelerating? If the answer is no, then I have, well, that fits for equilibrium, but that is not sufficient. I need to also check, is it having an angular acceleration? If that answer is no, then it's in equilibrium, right? You have to have both of those be no's. If either one's yes, it's not equilibrium. So you need to be able to identify, is this an equilibrium or not? And then if it's an equilibrium, you have these two equations. And then you need to be able to apply them. So this was where we first learned torque, and we had the equation for torque that said torque vector is equal to r vector cross f vector. Now, some things to note. This is not equal to force vector cross r vector. It's not equal because the direction is the opposite direction if you reverse the order in the cross product. Remember the right-hand rule, which I'm going to go over in just a minute. So this second one, this is not the right equation for torque. That's going to give you the wrong direction, the opposite direction. Second thing, and I actually had this on, a student wrote this on the last test, that work was force cross distance. That is definitely incorrect. Work is force dot distance. There is a very distinct difference between those two. The cross product means you're multiplying perpendicular parts. The dot product means you're multiplying parallel parts. So it's a mathematical distinction that's like getting a plus sign confused with a minus sign, right? They're not the same. So all through grade school and high school, well, not all through high school because we may have learned cross products and dot products in high school. But up until that, you used an X or a dot to both mean multiplication. They don't both mean the same thing when you get to vectors. So that definition for torque with the cross product, we have to be able to use our right-hand rule to find directions. So practicing, anytime you have a cross product, the cross product could be, A vector equals B vector cross C vector. I don't care what the vectors are. When you do that, it's always going to be that you take your right hand and the first item in the cross product is the index finger. So you take your right hand, orient it so you can have your index finger pointing straight and in the direction of that first vector. The second item in the cross product needs to be a direction that you can bend your middle finger to while keeping the index finger pointing that same direction. So if my index finger is pointing to the back of the classroom, I could rotate my hand all around like this, and of course my fingers can go like that as well. And then your thumb needs to be perpendicular to both the index finger and the middle finger because the cross product's direction is always perpendicular to both of the two original numbers or vectors. And so that's your thumb. So make sure you can do a cross product and find the direction from it. Also, there's just the magnitude, which I think is in the equation sheet. The magnitude of the torque is RF times sine of the angle between the two. Why sine of the angle between the two? Because I need to find the perpendicular component, so sine is the one that would give me the perpendicular. So I know I spent a lot of time here on torques, but it's an important concept here is understanding what the torque is. The last thing on this page for chapter 9 is making sure you understand the conditions for stable, unstable, and neutral equilibrium. So to put it in simple terms, stable equilibrium means if you displace it just a small amount from the equilibrium position, it will come back. So you can think of it like if I have a marble on a ramp of some sort, and the ramp could be like, this. And so if I have the marble right here, if I displace it just a little bit to the left or the right, we know that it's going to roll back downhill and come back toward its original position. Why does it do that? Because it goes to lower potential energy, and potential energy for that marble is mgh. So if I displace a little, it comes back. What kind of equilibrium does that make this position? Stable. Now let's say I have the marble here. If I push it a little bit left or right, what does it do? It falls away, so that makes it unstable. It can be equilibrium if it has a level surface for that small little region. But if you displace it anything from that that specific point and it goes away, it's unstable. And then finally, this is supposed to be a horizontal line. If I displace it a little bit from that starting position, it just sets up a new equilibrium in the new position, and so that's what we call neutral. So there's just a review on what the different types of equilibrium are. Now let's do a problem, a very standard type of equilibrium problem that really should come into focus here. So NFL rules. Hope you all watched the Raider game yesterday. It did, just about kill me again with their missing 2 field goals and everything, but they won. That's all that really matters in the end. Nobody remembers how badly you played. So NFL rules specify that you have the football goalposts that are 18.5 feet wide, 10 feet off the ground. You have the standard that goes into the ground 2 yards behind the back of the end zone. And you have it buried, that single standard, so it's buried 53 inches into the ground. Right? Those are the rules for goalposts in the NFL. And so back when I was in college, we have the Apple Cup where Washington State and Washington play, which, this year could be deciding who wins the Pac-10 North, since we're both undefeated in the Pac-10 North. Or in the Pac-10, actually. Pac-12. You can tell how old I am. So after the Apple Cup, when the Cougs beat Washington, go Cougs, the fans all rush the field and they climb on the goalposts. And, of course, one fan on the goalpost, it can probably withstand. But when you get a whole bunch of fans on there, it breaks down. Then the fans triumphantly drag the goalposts out of Martin Stadium, down Stadium Way, and deposit in front of a bar. But what I want to look at here is simply, that is not my phone. Specifically, looking at how much additional force is necessary to keep the goalpost up if you have one person who stands at the corner. So one person is going to be right here on the goalpost. So as you look at a problem like this, of course, the first question is, what's the physics involved? And by virtue of where this is placed, this is supposed to be an equilibrium problem. Otherwise, he would have put it somewhere else. On the test, you don't have that luxury. So you have to look at this and say, well, we want it to withstand that person, so that means it's not going to be falling over. Hence, it must be an equilibrium. So you first go through and you justify, this is an equilibrium because of this. Then because it's in equilibrium, I know I have my two conditions. Sum of the force vectors is going to have to be 0, and sum of the torque vectors has to be 0. And so I'm going to take those and go to town. So if I'm going to use these, I need a free body diagram, right? What is the object I'm going to do my free body diagram on? I'm going to do it on the goalpost, on everything that's yellow in this picture, plus the part that's buried under the ground. So I'm going to need to put all those forces that are acting on it. Now I drew two pictures here, a top view and a side view. So the top one's looking down. I put in red the person that's on the goalpost. And I did this because it helps me to work out the geometry I need for my second picture. The side view is the one I'm actually going to use. That's where I'm going to put my free body diagram. What is the side view showing? It's showing where the vertical post is, and it's showing where the person's additional weight is. And so then I'm going to put the free body diagram for this structure. So what forces will I have on my side view? Tell me. Gravity. Now, just to make sure I didn't read the whole problem, this says additional. So I am actually going to treat the goalposts as if they have no mass because I'm only looking for the additional caused by the person added to them. So it's just going to be the force of gravity. The person is my additional force. So gravity always acts what direction? Down. Okay, so there's one force acting on the goalpost. What's another force? Okay, a force normal, and there would be, I guess I better change color. There would be a force normal pushing up on the bottom here of the goalpost, right? We don't know its value per se, but if we use some of the force in the vertical directions, that there are only going to be two vertical forces, so we'll be able to get it real quick.
A force normal on the fan from the goalpost?
That's not acting on the goalpost. That's acting on the fan. Okay, we actually have what we call in physics a couple for the force on the ground. A couple because there are two forces, one that's at the surface and one that's at the bottom. And so to counter the torque created by that person, what direction would the goalpost rotate if I just have that person sitting on the goalpost? Okay, so it would cause a clockwise motion. So I need my forces to create a torque that's going to oppose that, that's going to cause a counterclockwise. So I'm going to need a force on the bottom that's going like that, and then I'll have a force here. Force, I'll put, now G is horrible. I am C just because it was available. So I have a force that's at the ground level and a force down below. So those two together would create a torque that's countering the torque of the person up there on the top. So I have all of the forces that are acting on this baby. There is one number, one distance that I don't have on the side view that I'm going to need. What's that distance? The distance from the fan to the vertical on the goalpost. That's why I put the top view. Because in the top view, we can see two different directions that are perpendicular in those directions, or those distances. So I can use the Pythagorean Theorem to say that R is equal to the square root of 2.819 meters squared plus, nice work, 1.829 meters squared. And since I see my good Jonathan working away, what do we get?
3.36.
Okay, give me one more digit.
0.
Okay, 3.360 meters. So I'm going to put up here that additional distance. Now, something I didn't mention, I gave you all of the distances above in feet and inches with 3 significant digits. And then I put all of my distances in meters in 4 digits. Why did I put 4 digits when I only had 3 significant? Yeah, to avoid rounding error. Because if I put an extra digit then when I go through and calculate my answer, I will have more digits that are significant, so I didn't take away information. And so I have, extra digits here again. So now that I have those, I'm ready to do my work. Which equation, I can solve this in one equation. That is, I can solve for either of the two forces, force C or force B, with one equation. Which equation would allow me to solve for either one of those with one equation? Okay. It's the sum of the torques. The sum of the torques because I just choose the right place to sum the torques, and I can make some forces cause no torque. And so I'm going to choose to use sum of the torques equals 0, and I need to choose a location to sum them about. So let us suppose that I want to first find the force C. If I want to find that force C, what force do I want to disappear? I don't know B and C, so which one do I want to disappear if I'm going to solve for force C? Force B. To make force B disappear, my torque equation, since torque is R cross F, the force isn't going to be 0, so I need the R to be 0. So if I sum the torques about any point that is on the line of action, the line that the force is on, it will make the torque 0 for that force. Now, technically, I don't know the force normal. We said it would be easy. But if I choose to sum them right here, then the force normal will also make 0 radius, and it will also make no torque. And so that's going to be my obvious place, and I'm going to label it B. So sum of the torques around B is equal to 0. So then I just add them up. So I'm going to have, just to be really clear, that's going to be force normal times 0 plus force B times 0. Now for the next one, I have to determine, is this a positive or negative torque? Use your right-hand rule. R is pointing from B to where the force acts, so R is pointing up. And then force C, I need to be able to bend my fingers in the direction force C. So I bend my fingers like, well, I'm probably bending the opposite, right, because I'm looking at my screen. So if I go here, R is like this, force C is like that. My thumb is coming out. Is that a positive or negative torque if the thumb is coming out? Positive. So it's going to be plus that distance, 1.346 meters, times force C. And then the last one is going to be the force of gravity there, which is mg. Now, is this going to be a positive or negative torque? We know if it's going to add to 0 what the answer is, right? But using the right-hand rule, my R points from B up to where the force acts. So my R is going up like this. And I need to orient my hand so I can point my fingers in the direction of the force. So like this, and my thumb points in. So it's negative. So minus that distance times my m, which is 95.0 kilograms, times g, 9.80 meters per second squared. I left blank the distance because I want to make sure we think about this. What does that distance need to be? Okay, it's the distance from B, but it's not just the distance from B. It's going to be the perpendicular part, the part of that distance that's perpendicular to the force. So we could, for instance, take this angle here, theta, and say that it's going to be that total distance times sine of that angle. Or we can be just a little more creative. Looking at our picture, since our force is vertical, the perpendicular distance is going to be the horizontal distance from point B to where the force acts, which is written on my picture. That perpendicular distance is 3.360 meters. And so finally, that whole thing was equal to 0. And so solving it out, force C is equal to that's a 95.
I get 2324. 2,300.
You get how much?
2,324.
Okay, so my intrepid student here got 2,324 newtons. How many significant digits do I have? 3. So the correct answer for this would be 2,320. If you just leave it like that, that's technically wrong. It needs to be units of newtons. Now that was force C. How should I find force B?
Sum the torques about the surface.
Okay, I could sum the torques about the surface. I could call this point C and sum the torques there, but there's now an easier way. Now that I've done this first step, there's an easier way. Newton's second law in the horizontal direction. Because we only have 2 horizontal forces. Those add up to 0. I can tell you right now that force B has the same magnitude but opposite direction. So that's an example of an equilibrium problem. It's a problem that I've actually put on tests before. Obviously, I'm not giving you a problem that I'm going to put on the test. That would make a mockery. Chapter 10, rotational dynamics. That was statics. Stationary is not necessarily what we were doing because equilibrium can be stationary or constant velocity, constant rotational velocity. Rotational dynamics now, we actually looked at kinematic equations for rotation and rotational equivalents. So the rotational equivalent for force was torque. Rotational equivalent for momentum was angular momentum. Rotational equivalent for mass, moment of inertia. We had all of these equivalents, so make sure that you know what's equivalent to what. It's not just useful to know, oh, there's an equivalent, but it also helps you to think about things. You know Newton's second law. And I had to mark up wrong. This is not Newton's second law, right? What's wrong with that? It needs to have a summation, and if you want to be perfectly correct, it's a vector equation as well. Right? You can put it as a scalar, but it's got to have the summation. If you just put F equals ma, well, it's not right. Okay, so if you know some of the forces, mass times acceleration, then you can say, well, rotational equivalent to force is torque. So some of the torques equals. Rotational equivalent to mass is moment of inertia. Rotational equivalent to acceleration is angular acceleration. So you can relate those, and in your mind it's not so hard because you have an analogy that you understood better, right? Because you learned it first. So make sure you know what these quantities are, what the symbols mean. Make sure you know the relationships like, angular velocity is equal to linear velocity divided by radius. So obviously you have those equations, but so you can do the conversions back and forth without having to trip over your feet or say, now, how do those relate? Make sure you know it. And then just solve problems. So solve problems like, we had the problem with the soup cans rolling down. Different moments of inertia. Now, when I did that demonstration, I did not say they had different moments of inertia. But after we did it, we looked at it and realized it was the different moments of inertia that caused the different speeds at the end. So let's just go straight to a rotational problem. Did we have this as a homework problem?
Yeah.
Okay. So with this problem, you have the yo-yo swinging around, and the first question is, draw the free body diagram that's correct. Now on the test, you're probably not going to have it ask you to draw the free body diagram. It's going to be the diagram you're going to draw as part of your solution. So just reminding ourselves, going back, last test, when you draw a free body diagram, what are the steps that go through your head? Molly? Okay, the first and most important thing is, what is your object? If you don't determine the object, you can't make a free body diagram, because the free body diagram is all the forces acting on a specific object. So you have to identify that object. So in this case, we look at the picture. What is our object? The yo-yo. So I'm going to draw the forces acting on the yo-yo. Then I just identify what the forces are, and so I'm going to have, pretty clearly, just 2 forces. Those 2 forces are, and go ahead and name them. Force of tension, which by rule is always parallel to the string in the direction it leaves. And the other one, force of gravity, which once again by rule is always what we define as the downward vertical direction. So there's my free body diagram. What is not on that some people want to put on there? Centripetal force. You don't ever put centripetal force on it because centripetal force is not an actual force. Centripetal force is the name for the sum of all the forces going toward the center when something's going in a circle. Right? It's a name for the sum. And so we're going to use sum of the forces toward the center is equal to mass times acceleration toward the center in this problem. Well, if I'm going to use that, I really need to define directions, don't I? So let's make sure we have that clear. It's going in a circle, the center toward the center of the circle. Now I'll just call vertical y. So there's Newton's second law. Sum of the forces toward the center is MAC. Or I could put sum of the force vectors is equal to mass times the acceleration vector, which is going to be AC in the direction toward the center. So we drew the free body diagram. The next question is to calculate the tension in the string. Calculate the tension. This is one of those problems where doing it graphically is going to be the fastest solution. Doing it graphically, Newton's second law gives me the force of gravity. That's supposed to be vertical. mg down plus the force of tension equals ma. And from our picture, we were given the the angle right here is theta s. So that means this angle here is also theta s. And so just looking at my diagram from Newton's second law, I can immediately see that I must have, what's the easiest way? Well, I always do it and calculate this first. But if I'm going to do it the way I'm going to calculate the angle first. So I'm going to calculate tangent of theta s is equal to the opposite side mg over the adjacent side m, and now I'm dropping the vector sign because I'm just going to put the magnitude of the acceleration there. And so I can find the angle that way real quick, and once I found that angle, then I can go, actually, there's a variable in there that we don't know, that is v, but v relates to omega. V is equal to omega r, and so I just put in omega r and I have it. Once I know that angle, then I'll say, I could use opposite and hypotenuse, that is sine of theta s is equal to mg over force tension. So that means force tension is mg over sine of theta s. Yes?
What did you get R?
R was given right here. Oh, is that? Oh, that's the race. Okay. I thought I was thinking it's the race in the circle. My mistake. Okay, so in that case, I actually have to draw myself a second circle. Or not second circle, but a second triangle. I need to have there's theta s there. And this is r of the string. And this is r. And so I can relate rs and r of the string with cosine theta. So now that does add a level of difficulty here in that I have cosine theta here, I have tangent theta there, I'm probably going to need to use some different trigonometric identities to get myself going. If I want to compare here cosine theta wait, I wanted R. Obviously, when I prepared, I didn't realize that they gave us the other R. So R is RS cosine theta. And then looking at this picture here, I have cosine theta is also equal to MA over the force of tension, which is and that gives me a rather convoluted equation. Cosine squared theta is equal to m v squared. Yeah, I'm seeing that my life would have been easier if I'd used the other equation. Equals. Right, that would have made my life easy to use right there. That centripetal acceleration is v squared over r, or omega squared times r, because then I'd have cosine theta on both sides. And so my cosine thetas I can now cancel. I suppose that must be why I had it in that direction. And solve this for force of tension equals that. And then once I have the force of tension, then I can go back and find the angle from sine theta s is equal to mg over ft and go on like I was doing. So I feel sad that I did not notice it was the wrong race. Yes?
Couldn't you just solve it by saying that some of the forces in the vertical direction is 0?
That still has two unknowns because we don't know theta s and we don't know the force tension.
That's true.
So we still have to go through something of this order. Yeah. Okay, so yeah, now I'm sweating because it wasn't the way I intended or I thought the problem went. So once we've done those two things, found theta and force of tension, the rest of this problem was just what happens if you increase this variable, decrease that variable. Since I do all my answers in variables, it's very easy to then say, oh, well, if I increase this, that's going to happen because it's in the equations. A second problem, again with a yo-yo, but distinctly different. We have a yo-yo that is hung by its string and falling, and it's asking us what the acceleration is. Now, the naive answer is, well, it's falling, so it's falling with an acceleration of g. But that's not correct. Why is that naive and incorrect?
Some of the energy goes towards rotation.
Okay, one answer is some of the energy is going to be going into rotation and some into kinetic. That's a correct answer. Another one, so that was a work energy type look at it. Another one is the net force is not just the force of gravity. It also has an upward force of tension. So we have to look at a picture here and show the forces that are acting on my object, the yo-yo. So in this case, I would have an upward force, the force of tension, and downward force on the center mass, the force of gravity. And notice I've defined up as my positive direction. And if you look at this, you could say, well, let's use Newton's second law. It's not in equilibrium. It's not equal to 0, but some of the forces in the y direction is MAY, which gives me force tension minus force of gravity is equal to MAY, but I don't know the force tension and I don't know the acceleration, so that's not enough. So I need a second equation. The second equation that I can make is the rotational equivalent. Some of the torques about the axis coming out of the wheel, which I don't have identified direction, is equal to I alpha. And so doing that, what's making a torque about that axis? Tension. The force of gravity is acting on the axis, so it's making no torque. But the tension is, so that's going to be the force of tension times the distance from my center to where the force acts, which in this case was 9/10 r. So that's the torque, is equal to I, 1/2 mass times radius squared, times alpha. Well, that's two equations, three unknowns. Acceleration, alpha, and force of tension. You need as many equations as you have unknowns. So I need one more equation. And the last one's a simple equation relating acceleration with angular acceleration. Now, you might notice I played fast and loose with my signs here. Continuing that fast and loose with the signs, my acceleration is angular acceleration divided by, and I can't just put radius because it's acting at 9/10 the radius. Actually, no, it is. Angular acceleration is the, yeah, it is going to be 9/10. And so now I have three variables, three equations. I can solve it. So using this, I can just plug in there. How's a perfect arrow? Plug in there to put it in terms of acceleration. And then between the red equation and the blue equation, I can solve for force of tension and for acceleration. What's different about the two situations? The radius at which the force is acting is different. Because the radius at which the force is acting is different, it potentially has a difference on the acceleration. Because I only have 8 minutes and 2 chapters to go, I'm not going to finish out the problem, but go on to chapter 11, fluids. Chapters 11 and 12 were chapters dealing with fluids. And with chapter 11, I started off just by making sure that we know the three common states of matter: solid, liquid, and gas. And as I pointed out, lots of times people say, well, you know, plasma is not uncommon. That's also common. A plasma is an ionized gas. Behaves differently because of the charge interactions. So, you know, the sun is a plasma. Today in my astronomy class, we're going to be playing that They Might Be Giants song. The sun is a miasma of incandescent plasma. So it is a state of matter. But the three that we really fundamentally care about for general physics are solid, liquid, and gas. So make sure you can identify the differences. What makes a solid a solid? What makes a liquid, and so on. And then which of those are fluids? So which of these three are fluids? Liquid and gas. The bottom two, because a fluid is anything that flows. If we were to include other states, a colloidal suspension is a fluid, a plasma is a fluid, right? Anything that flows, fluid. And we talked about technicalities. Is glass a fluid? Well, technically it flows over a very large amount of time, but everything flows over a very large amount of time. And so we use reasonable definitions and say, no, glass shouldn't be considered a fluid. It should be considered a solid. It's a, not a crystalline solid, but an amorphous solid. Okay, then we had two principles here for static fluids. Pascal's principle that said the force at the same elevation in a continuous fluid that's stationary is going to be, or the pressure, excuse me, is going to be the same. So that was Pascal's principle, and we use that for things like explaining how a hydraulic ram works. Of course, you have to have in your head that pressure is force over area, and wherever your source is, or your object is, the pressure will put a force that is going into that object normal to the surface at any point. Right, so my little red arrows are showing, that was not, the direction the force goes into a surface because of a fluid with pressure P acting on it. Archimedes Principle, that was the one that dealt with buoyancy. Archimedes Principle said that the weight of displaced fluid is equal to the buoyant force. In our lab last week, you tested that to see if it was true. Did you find it to be true? I pray that you did, because literally millions of people before you have tested it and found it to be true. This is where we started paying a lot of attention to density. Density is defined as mass divided by volume. So that means we can put the mass in terms of density and volume. So the weight of the displaced fluid is going to be the mass of the fluid times g, which is going to be density of the fluid times the volume times g. Now, we had two more things to think about when we were dealing with floating or sinking. If it floats, of course, Archimedes' principle is still true. The weight of the fluid displaced is equal to the buoyant force. But we also have, if it floats, the buoyant force is equal to the weight of the object. Were it not so, you would have the object either accelerating upward or accelerating downward. So it makes very good sense that if it floats, the buoyant force is equal to the weight of the object. If it sinks, that's not going to be true, right? It accelerated downward until it hit the bottom, which meant that you had a greater downward force than upward force. But if it sinks, the volume displaced is equal to the volume of the object. So if something sinks, you're going to have, in addition to Archimedes' principle, the equation that the volume of the object equals the volume displaced. If it floats, in addition to Archimedes' principle, you have the weight of the object is equal to the buoyant force. So any problem that you solve with Archimedes' principle is going to require you probably to use one of those two as well. So let's take an example here of a flow. Actually, we have 3 minutes left. Let's look at chapter 12 and then come back if we have time. Chapter 12 is fluid dynamics, moving fluids. So we had the flow rate. I showed you both the mass flow rate and the volumetric flow rate, the difference just being multiplying both sides by density. In our work, the density isn't going to be changing, and so we're just going to talk about the volumetric flow rate. So that is Q is equal to the area times the speed. And if I have a contained fluid and it's flowing in a laminar fashion, the flow rate throughout should be constant. So I go from a bigger pipe to a smaller pipe, the area got smaller, the speed has to increase. Then we have the Bernoulli relation, Bernoulli's equation here, that says if the speed decreases, what happens to, or increases, what happens to the pressure? It goes down. So if I have a pipe like this and I have fluid flowing through, because the speed is faster over here, it has a pressure that's lower. Slower over here, it has a pressure that's higher. Oftentimes that can be confusing. Back when I was a member of the Anglican Community Ambulance, our everything, he's the second highest official in California highway patrols now. Avery Brown was teaching on the circulation of the body and talking about, when a person is scared, why the, the arteries constrict and whatnot. And he said, because that increases the pressure. Well, when the blood goes through the constricted artery, it goes faster and it decreases the pressure there. But what it does do is increase the pressure upstream of where it constricted. And so he kind of had it backward, but it's because he was not a physicist. So with our fluid dynamics, make sure you understand the difference in turbulent flow and laminar flow. We didn't do any actual work with turbulent flow, but we talked about how that Reynolds number is calculated, and it can be used to predict if you're going to have turbulent flow or laminar flow. So you should understand why you have the differences in the two, understand what laminar flow is and what turbulent flow is, and of course, the viscosity. That's weird. The screen just went out on the system going over to them. Okay, we only have 10 seconds left. if you're going to solve this problem to find what percentage is above water, you're going to have free body diagram, force gravity down is equal to the mass of the iceberg times g, or the density of ice times the volume of ice times g. And you would have the upward force, the buoyant force, is equal to the density of the water times the volume displaced times g. And if it floats, those two forces are equal, so you just set them equal. Density of water, volume displaced, g is equal to density of ice, volume of ice, g. I asked for what proportion is, I don't know if it was below, above or below, but let's just put the volume displaced divided by the volume of ice equals, so I had to divide both sides by volume ice. And to get them by themselves, I have to divide them by density of water. And there's how you get your answer. Okay, we are now 7 seconds over time. So we'll have normal lab time tomorrow. The exam, I will move that homework 26 so it's not due until Wednesday. I made a 22 problem, very small amount of extra credit homework assignments so people could practice homework problems before the test if they so desired in response to requests.